Okay, in this video I'd like to continue on my tutorials in thermodynamics and statistical mechanics. This video number 39, and I'm going to talk about the Gibbs and Helmholtz thermodynamic identities. I'd like to draw your attention to my website universityphysicstutorials.com. So the previous videos to this are number 39, where I discussed the chemical potential, 38 where I discussed the Gibbs and Helmholtz free energies, and number 36 where I discussed the thermodynamic identities in terms of the total energy, the chemical potential, temperature, pressure, the internal energy and volume. So now what we're basically going to do is get our own thermodynamic identity for Gibbs and Helmholtz free energies. So just to remind us, the thermodynamic identity said the infinitesimal change in the internal energy is TdS minus PdV plus mu times dN. That's what it is. Alright, so we also knew that the enthalpy, H, is equal to U plus PV. So basically what I'm going to do is just manipulate U plus PV and get DH. Alright, so we know that H is a function of internal energy, pressure and volume. That means that DH is equal to del H, del U du plus del H, del P dP plus del H del V dV. In general, that's just that is just a a mathematical property of all these derivatives. Okay, so that means DH is equal to du plus V dP plus P dV. Okay, if you just plug in the derivatives, or DH is equal to TdS plus VdP plus mu dN. Okay? That is the thermodynamic identity for enthalpy. Next, we're going to do the thermodynamic identity for the Helmholtz free energy F. Well, the Helmholtz free energy is when you're at constant temperature but not constant pressure. So F is equal to U minus T times S. Similarly, say F is a function of U, T and S. Okay, so that means that dF is equal to del F del U du plus del F del T dt plus del F del S ds. Okay, so the derivatives are pretty straightforward. So when you plug in the derivatives, you're going to get that del F is equal to du minus T ds plus, or excuse me, minus S dt. Like that, minus S dt. Okay, now what we're going to do now is, we know that we have du, we can furthermore plug in du because we already have what du is here. So we're going to get that dF is going to be equal to TdS minus PdV plus mu dN, and then we're going to have our two other terms of negative TdS minus S dt. Okay, so we can see pretty straightforward that we have this TdS term cancelling here, and that leaves our final thermodynamic identity for the Helmholtz free energy. Says that dF is going to be equal to minus S dt minus P dV plus mu dN. Okay, so that is the thermodynamic identity for the Helmholtz free energy. Okay, next let's look at the Gibbs free energy. So this time we're at constant pressure and constant temperature. That's going to be equal to U plus PV minus T times S. Okay, so look, we know what dG is at this stage, you've done it 20 times, but if you plug in all the values, you get dG is equal to du plus VdP, and another helicopter flying over me. Okay, so we get that. Once again, we're going to plug in for our du, so we get TdS minus PdV plus mu dN. we're still going to have our other terms of VdP plus PdV minus SdT minus TdS. And that's going to give us the infinitesimal change in the Gibbs free energy. And we put it all together, saying that the infinitesimal change of the Gibbs free energy is minus SdT plus VdP plus mu dn. Simple. Okay? Now, one last thing to show you. If we look at dF, so let's just first of all write down dF. The reason these are so good, these are so useful. Let's say if we wrote down dF, like I said, the physicists would prefer to use the Helmholtz free energy, which is constant temperature, because it gives the extra degree of freedom with pressure. So F, or dF, excuse me, as we said there a moment ago, was minus S dt minus P dV plus mu dn. Now let's look at the partial derivatives here. So if we hold, for example, the volume and the number of particles fixed, we get entropy. Entropy is minus del F del T if we hold the volume and the number of particles fixed. We know that the pressure is going to be equal to minus del F del V at constant temperature and number of particles, and we know that the chemical potential is equal to del F del N, where we hold the temperature and volume fixed. Alright? And similarly, you can do the same thing, I suppose, with your Gibbs free energy, and we're going to get the following relationships: that S is equal to minus del G del T, holding the pressure and number of particles fixed. We know that the volume is equal to del G del P, holding the temperature and number of particles fixed. And we know the chemical potential is equal to del G del N, holding the temperature and pressure fixed. The point here is that by measuring the Gibbs free energy or measuring the Helmholtz free energy, you're able to get these quantities of entropy and chemical potential and, for example, volume or pressure. And that's something which is very easy to do. In the lab, we're able to control things, like we're able to control, let's say here, we're able to control temperature, definitely. Pressure, absolutely, we're able to make the two of those constant. I said earlier on in a previous video that to hold the pressure constant, you just don't put a lid on your apparatus. And by measuring the rate of change of the Gibbs free energy with the number of particles, you get the potential, or the chemical potential. Alright, so that's why these relationships are so useful, and that's why we talk about the the free energy, which is the amount of energy you get back in terms of available for work when you destroy or annihilate a system. Finally, by going from VdP to PdV can be thought of a change of variables, which we call transforms. And you can speak about the Legendre transforms, and that's going from VdP to PdV. But I don't really want to use that, if I'm honest, but it's just in case you haven't heard of it. So thanks for watching. Please pass it on to your friends, subscribe to my channel, and please also visit universityphysicstutorials.com.